Okay, Boyle's Law. Let's see. We did one problem, right? We did one problem. Which problem did we do? Okay, we did that problem. Is that the first problem?
That's the second one.
Oh, that's the second one. Okay. So there's the third one. Oh, moving too fast. There's the third one. You want to do that one right now? Just do that one right now. Just kind of get warmed up here. Remember, read the problem. Read it again. So you should read a word problem. You take a tease test or something. Don't rush through this part of it. Read the problem and then read it again. So many times, students answer the wrong question. You know, they go ahead and they say, "Oh, I know what this is all about." And they do it, and they get an answer, but that's not what it's not what the question was asking. So you need to look carefully at what it is asking. You'll see this in the ideal gas law. You may think, oh, they want to know the amount of the gas, and you calculate the amount of gas and you report it in moles. But the problem said, how many grams of oxygen was in that container? Not how many moles, how many grams. All right? You get almost to the right answer, but you don't get all the way there because you didn't read the question really carefully. So read it carefully and then label it. Label what you got, what you don't have, and then solve it. I'll just give a minute or so. So dive into it. We'll get into Charles' Law. Let's see, Andreas, Chloe's here. Chloe, Viviana,
Here.
Lucas,
Yes.
Mark,
Here.
Michelle, Jean, just walked in. Natalie, Melody, Christy, Ashley,
Here.
Amanda,
Here.
Joel,
Here.
Alejandra,
Here.
Daniel,
Here.
Ashley Nieto,
Here.
Tasneem,
Here.
KK,
Here.
Adrian, Shantae, Hannah,
Here.
T, and Egypt. All right. I don't know if you could concentrate on this with all that talking of mine, but all right, so this is a Boyle's Law problem. So you should bring up Boyle's Law. Start there. There's 4 things. And usually in these problems, you're going to have an equation and you're going to be missing one thing. Typically you got to be given at least 3 of these. If the gas originally at 1 atmosphere is now at 0.5 atmospheres and 0.3 liters, what was its original volume? V1. So this volume over here has to be what? 0.3 liters? V2. So we have a situation where V1 is our unknown. You can see that's what I drive for right away. What do they want us to calculate here? And so then you have everything else. This is 0.5 atmospheres. These have 3 significant figures in them. All right, so we want to get V1 all by itself. Remember, you can do whatever you want. This is algebra. When I say algebra, okay, this is college algebra that we use continuously in this class, algebra. You can do the same thing. You can you work on these equations as long as you do the exact same thing to both sides of the equation, you maintain the equality. So I've divided both sides of the equation by P1. And that has maintained the equality. So P2 is 0.50. You see that? I was almost going to put the wrong pressure. And that's easy to do because it is a pressure. But you need the P2 in the numerator and the V2 in the numerator and the P1 in the denominator. There's my dimensional analysis. And what's the answer?
0.15.
Is that right? Is that what everybody got? 0.15. Okay. All right. Okay, now let's take a look at Charles' law. Charles' law. Boyle got famous, so Charles said, okay, I'm going to look at volume and temperature. Volume and temperature. Notice up here that the pressures are all 1 atmosphere. So the pressure is constant. And the other thing that's constant here is the amount of the gas. He puts a certain amount of gas in to begin with, 1 liter of gas, of an ideal gas. And he doesn't, see, we don't even need to know what the gas is. He just got a liter of an ideal gas. And he's not going to let any of that gas escape. He's got an apparatus here where we'll seal properly and not let any gas escape, not let any other gas get in there. And what is he doing? He's changing the temperature. He's changing the temperature. And he's looking at the relationship between volume and temperature. And you can see the temperature is in Kelvin. So he starts out over here. This is condition 1, condition 2. So you've got V1 over T1 equals what? You've got 1 liter divided by 273 Kelvin. Now V2 over T2, you have 2 liters divided by 500. He's doubled the temperature. That's what this is. 273 times 2 equals 546 degrees Kelvin. So he has doubled the temperature in Kelvin. And what happened to the volume? It doubled. The volume doubled. All right, so if I were to divide this by 2 and divide this by 2, I would have 1 over 273. Right? The ratio hasn't changed. It's still 1 to 273. And then if we went over here, he has doubled that temperature. 546 times 2 is 1,092, so it's really 4 times this original temperature. So we've got 4 liters over a number that's 4 times the original temperature. So this one is also going to come back down to that same ratio, 1 over 273. So what Charles found out is that volume over temperature is a constant. Doesn't vary. You get that relationship, volume divided by temperature. And what we would also say here in word terms is that The volume is directly proportional to the temperature. What does that mean? You increase temperature, you're going to increase volume. They move together. You increase the one, the other one's going to you increase temperature, it's going to increase volume. We didn't see that with pressure. Pressure and volume, in Boyle's law, pressure and volume are inversely proportional. You increase the pressure on a gas, and what do? You decrease the volume. The volume goes in the opposite direction. So that's where we say they're inversely proportional. You increase the one, the other one decreases. But not in Charles' law. You increase temperature, you increase volume. That's a direct proportionality. I hope I don't, yeah, here we go. Direct proportionality. So V1 over T1 equals V2 over T2. We're taking this right here. So it doesn't matter where we look at this. Anytime we look at this, it's going to be what it was to begin with. It's not going to change its value. This ratio is going to be a constant. So there, you are familiar with a lot of direct proportional relationships between variables. The further you drive, the more gas you burn, right? The amount of gas you burn is directly proportional to the miles you drive. The older you get, when you're, from 1 to 12, let's say, or 1 to 18, age 1 to 18, the older you get, generally, the taller you get. Your height is directly proportional to your age. And then it kind of plateaus off there. If it doesn't plateau off, you're going to end up playing for the Spurs. Okay, if it just keeps going, you should start learning how to bounce basketballs. If you think that's going to go on forever, start bouncing basketballs, and you'll, if that's what you like to do. Okay, so there's a direct proportionality. Temperature is increasing, volume is increasing, and you get a straight line plot. And that is our expression for Charles' law. Charles is dealing with volume and temperature. Boyle, pressure and volume. All right, now these are going to be a little more. So here's a Charles' law problem. A gas at 25 degrees C and 3 liters is heated to 100 degrees C. What is its volume at this higher temperature? Okay, I said read it twice. A gas at 25 C. So we have this law. So as we read this now, knowing that it's a Charles' law problem, because I told you that, just keep in mind, you won't be given that information routinely. So if you read this and you see, well, all I see in here is I see temperatures and I see volumes. Boink points you in this direction. It's not a Boyle's law problem. We're assuming, now it should actually say here, but assume that pressure and the amount of gas is remaining constant. We're not changing the pressure or the amount of gas. The only thing changing here is what they're telling you about. So 25 degrees C, which one of these is that? It's temperature 1. 3 liters, volume 1, is heated to 100 degrees C. Temperature 2. What is the volume at this higher temperature? Okay, what is this volume? So that is our unknown, right? Okay, you have to understand English. You have to be fairly good with English as you're reading these problems. You need to know what is a past tense verb and a present tense verb so that you kind of know, oh, this is talking about at the start, this is talking about later. It's heated to 100 degrees C. So volume 1 is 3 liters. Temperature 1 is 25 degrees C. Is that okay? 25 degrees C? No.
Gotta convert.
Got to convert. Did I say? You have to convert to Kelvin. So we have to add 273 to this. T2 is 100 degrees C. We have to convert. All right? In any gas law problem, you see temperature, use Kelvin. Doesn't matter that you're given centigrade. I won't be giving you Fahrenheit. I'll be giving you centigrade or Kelvin. And why do we stick with centigrade? Well, that's what the thermometers are in the lab. So that's what you're going to be reading on a thermometer. But you have to know, this is a gas law problem. I can't use that temperature. I have to convert it. Okay, now we got to isolate. What do we have to isolate? V2. So what do I have to do to this equation? I'm going to move it over here. How do I get V2 all by itself on one side of the equation? Yes. You could cross multiply. You could say that this law is this. Okay? You could express this law that way. By cross multiplying these, you could get a new expression that makes it start looking like this. It's easier to manipulate. So I'm going to leave it up to you. But I just kind of want you to see that this is V1 T2 equals V2 T1. Let me just show you how we get there. Let's multiply this by T2. Let's divide. Let's multiply this by T1. Well, so we got T2 V1 equals over T1 equals V2. Well, let's multiply this by T1. Both sides of the equation by T1. And that's basically cross multiplying. All right? That's cross multiplying. So you could do that. You could just simply multiply this by T2. Yes? We're going to get to the same point, because if we started right here, if we want to get this all by itself, we still have to divide by this, don't we? We still have to divide here, because we want to get this by itself. And you end up at the same place. Okay? I'm running around on the board here pretty fast. I hope you're following me. But I'm just doing some algebra here. But we eventually get right here. Let's put it on this. So, all right, so slow down over here. I want to get, V2 is my unknown. I want a question mark right there. V2 is my unknown. I want to get it by itself. So I'm going to multiply both sides of that equation by T2. And I get V2 equals V1 T2 divided by T1 So what is that? That's 3 liters times T2 is 373 Kelvin. Okay, you need to pay close attention to get your right temperature in the right place. Divided by 298 degrees Kelvin. Kelvin is going to cross out and leave the units of liters. That makes sense. We're trying to calculate a volume, right? All right, so what is the answer here?
3.75.
3.76?
Yeah. It's 3.7. I rounded it off.
Rounded it off to 6?
Well, but like if you do just 3 significant figures, you don't have to round, right?
Well, but if there's a 5 after that third significant figure, you have to round it up.
Okay.
3.76.
Doesn't sound as good.
Yeah. You like to, yeah, when you round off, you're really trying to round off. So what happened? Our 3 liters went to 3.76 liters. Okay, now I want to do this one more. I'm going to do this one more time for the skeptic in the audience, the person in the audience that says, "What's this change in temperatures?" It should come out the same if you use centigrade. Okay, let's go back. Remember centigrade. We had 25 C over 100 C. So let's just say V2 equals V1, 3 liters, times 100 degrees centigrade, divided by T1, 25 degrees centigrade. Centigrade still crosses out. Here's one time where dimensional analysis isn't going to save your day. Because this crosses out, you go, oh, everything looks fine. What's the answer to this equation? 12 liters. If you leave it in centigrade, what does it look like? It looks like you quadrupled the temperature, doesn't it? So 4 times 3 is 12. But you didn't quadruple the temperature. You just, in terms of Kelvin, the absolute temperature scale, you didn't quadruple it. You didn't even double it. You just incrementally increased it a bit. Yeah, you increased it 75 degrees Kelvin, but it started out at 298 and it went up to 373, and you only got a slight change in volume. Not this 4 times. You see? I like this problem because this problem just nails it. You've got to change it to Kelvin. You won't get the right answers in centigrade. And why is that? Kelvin is the absolute temperature scale. It is the temperature scale that is directly proportional to the energy that the gas molecules contain. At 0 Kelvin, they have 0 energy. At 10 degrees Kelvin, they have some energy. Not a lot. A little bit of energy. But at 298 degrees Kelvin, they have a lot more energy. But the centigrade scale doesn't index off of energy. It's related to the freezing point and boiling point of water, not the absolute energy that they have. Okay. Okay, let's pause this for a second. Let's do a Charles Law problem, because that's not quite ready for me. Do this problem. Is this the same problem?
No.
Yeah.
No, it's different.
It's different.
It's the same numbers.
So you're looking for initial gas.
Okay, okay. Oh yeah, half of you already got it all done. Good. You got that one done, do the next one. let's take a look at this one. Let's start with it this way. Do you like to start this way? Is that the way you like to start it?
Yeah.
In the cross multiply? Okay, it is easier. The beauty of this one, I do think the beauty of this one is that you've gotten the temperatures out of the denominator. And that helps you. So let's start out with Boyle's law, or Charles' law, being this. Just know that this is equivalent to that. There's nothing, we haven't changed the law at all. It's equivalent to it. What was the initial volume? A gas originally at this and heated to this occupies this. So V1 is our unknown. T1 is 25 plus 273, 298 degrees Kelvin. V2 is 3 liters. T2 is 373 Kelvin. Okay, now there's a problem where they actually mixed up centigrade and Kelvin. They got one of each. We want to know V1. So we need to divide this side by T2 and this side by T2. And it gets my V1 all by itself. And what's the answer to that? That coming out as point
2.40.
2.40.
2 what?
0.40.
Okay. All right. So yeah, this is fine. So if you want to in your chart have Charles' law in this form or this form, whichever form helps you. We're not going to. Is it steaming yet? Ooh, that's hot. Okay. All right. Let's just take let's take a minute here and just combine gas law. And I'm not. I don't think we're going to get down into. We'll just kind of start a problem here, but. Combined gas law. There's the Boyle's law, Charles' law. You bring them together and you get this thing. That P1 over V1, there's Boyle's law, divided by T1 equals P2 times V2 divided by T2. That's going to be a constant. That's the combined gas law. You're combining Boyle's and Charles' law into one law. And let's see if I have an example. Do I have a weather balloon example? I don't think so. No, weather balloon. Well, let's... okay, these get kind of complicated. Without even reading this, look at... I'm going to put this atmosphere over here. I've got 1, 2... I'm going to put the liters over here. 3, 4, 5 things in here. And they're asking you for a 6th one. That's the combined gas law. Now, if you cross multiply, you end up with, that's the combined gas law. But if you cross multiply, I'm going to cross multiply. I'm going to get P1 V1 times T2 equals P2 V2 times T1. Is that the way you like it? Okay. We'll get everything out of the denominator. And what do we have here? We got combined as P1 V1 T2 equals P2 V2 T1. I'm not going to get bogged down in all this calculation. Let's just analyze this problem, and then I want to go on. What is the final temperature? T2. T2 is my unknown. So T2 is my unknown of a gas that's at 50 atmospheres. Okay, this is P1 and 0.320 liters. This is V1. That initially I'm sorry, I'm off. What's wrong there? What is 50 atmospheres?
P2.
All right, it's describing the final temperature of a gas that is at 50 atmospheres and 0.320 liters. All right, so we got a key off of this word right here. It's describing final condition and everything that goes after it. See, I told you have to read these slowly. I just proved it. You got to read them slowly and slow down, or you'll make mistakes. Or I'll make mistakes. Anybody will make mistakes if you try to do this too fast. What is the final temperature of a gas, T2, that's at 50 atmospheres, P2, and 0.320 liters, V2, that initially, okay, now this is starting to point to condition number 1. Initially occupied 1.27 liters. How do I know that? How do I know that's a volume? How do you know 1.27 liters is a volume? The unit. Liters is a volume. So the problem doesn't tell you that's a volume, but the unit does. At a pressure of 5 atmospheres, so this is P1, and a temperature of 149 Kelvin. All right, as far as I'm going to go here is just rearrange the equation. We're trying to calculate T2, right? This is what we want to calculate. So what do I have to do to the combined gas law to get T2 all by itself?
Divide P1 and V1.
Divide this side by P1 and V1, which means I have to divide this side by P1 and V1. P1's cross out, V1's cross out, and we get T2 equals that expression right there. All right, now you're ready to solve the problem. You can punch in the numbers. All right, I'm going to leave this for you, and there are other combined gas law problems here. Do these. These are a little bit more complicated because there are 6 parameters here. Okay, before I get to the ideal gas law, I'm going to just mention Avogadro's. I'm going to just mention it. Avogadro's law. Avogadro looked at the relationship between volume and the amount of gas the moles of the gas, the amount. And what he found, well, let me give you a real practical example. You've all done this. How many of you have ever blown up a balloon? Somewhere here I used to have some balloons, but I don't think I got them with me. All right, but just imagine. Okay, we'll do this. This will be imaginary, because you know balloons. You take a balloon, you fill your lungs with air, and you blow into the balloon, and it gets maybe that big, all right? You do that again. You add more air to the balloon. What happens to the balloon?
It expands.
It gets bigger. That's basically Avogadro's law. The greater the amount of gas, you increase the amount of gas, you increase the volume. So the moles of gas and the volume of the gas are directly proportional to one another. So V1 over N1 equals V2 over N2. Just like Charles' law, where it's V1 over T1, they were directly proportional to each other. You increase temperature, it increases volume. Well, if you increase the amount of the gas, you increase the volume of the gas. If you keep the pressure and the temperature constant. That's Avogadro's law. I'm not going to get into those. So V1 over N1, or if you cross multiply, you have V1 times N2 equals V2 times N1. That's just a rearranged expression of this law right here, Avogadro's law. That little thing go. There it is. It's Avogadro's law. We won't do a problem there. But now look at what we've got here. Now at this point in time, with Boyles, Charles, and Avogadro, we have introduced all of these variables that I pointed out to you when we started this chapter. I said gases are going to deal with pressure, volume, temperature, and the moles of gas. So we got Boyle's law showing that PV equals a constant. Charles' law, V divided by T equals a constant. Avogadro's law, volume divided by the moles is a constant. Now let me take a look at that right there. So what we've got here, here's Boyle's law. Pressure times volume is a constant. Charles' law, volume divided by temperature is a constant. Avogadro's law, volume divided by the amount of the moles is a constant. And they named this constant after me. I love it. That's why I have an ideal gas law shirt. R. They didn't name it after me, but that is the symbol for the ideal gas law constant. And it is, you're going to see in a moment, it is a real number. It's a real number. And it's got all the laws in there. Now notice what happens here. If I want to just rearrange this equation a little bit, I could take this equation and multiply it by NT. N's cross out, the T's cross out, and I get PV equals nRT. All right? So that is the normal way that you see the ideal gas law expressed. PV equals nRT. But I wanted you to see that it's coming right out of these three laws, all put together now. I'm not going to say combined, because combined just has to do with Boyle and Charles, but this really is bringing all three laws together, all four variables that affect gases together into one equation. Oh, P here. All right, PV equals nRT. Now, let me point out some other interesting things about this. On every one of these laws, we were saying, okay, we started here, we ended here. So what was our V2 or whatever we want to calculate? You know, we started here and we want to figure out what the original temperature was. We started here, we ended here. This one isn't a initial, final. It's kind of like right now, I've got a gas. There's a certain amount, it's a certain volume. It's a certain pressure. It's at a certain temperature. Now I can calculate how many moles of it I have. Adrian was mentioning the oxygen tanks. And the oxygen tanks are about 1,500 pounds per square inch. And I'm dividing that by about 15 pounds per square inch is 1 atmosphere. That's 1 atmosphere. So you divide that in there, you got about 100 atmospheres, pressure. So you got a cylinder, and it's at 100 atmospheres. It's at room temperature, 20 degrees centigrade. It is, you got the pressure, the temperature, the volume. Let's say it's 35 liters. I can now calculate how much oxygen is in that tank with that law. I'd say, how much oxygen is in that tank? How long is that oxygen going to last? How much does it weigh? All right? Because I've got a pressure, I've got a temperature, I've got a volume, and what I don't have is the moles of the oxygen. I could calculate it with this law. That's the beauty of this. This is a robust law. If you know any 3 of these 4 parameters, this one you always know because it's a constant. If you know any 3 of these, you could calculate the 4th one. And that's what we want to do right now. All right, let me point one other thing out. Here is the ideal gas law constant. It's on the back of your periodic table. It may or may not say, actually the one I give you on the exam does not say that it's the ideal gas law. It just says gas constant. It doesn't have R.
Yes.
This one is a little bit different from your just in that one spot. Doesn't have R. Okay, Daniel, take a look at it. See the difference? Okay? So just know that the gas constant is R. And notice it has units. So R, the units of R are liters, atmospheres, per mole, Kelvin. Notice this, liters, atmospheres per mole Kelvin. So it has the same units that those parameters have. All right, so when you do an ideal gas law calculation, you got to make sure your temperature is in Kelvin. You know that. You know that for all gas laws, but for ideal gas law, you have to the amount of the gas needs to be expressed in moles. The volume of the gas needs to be expressed in liters, and the pressure of the gas needs to be expressed in atmospheres. So if you're given a pressure in millimeters of mercury, you have to convert it to atmospheres to do an ideal gas law calculation. All right, so this is now let's just read this and see if we could figure out that this is an ideal gas law problem. Calculate the moles of a gas is at 27 degrees centigrade, 1 atmosphere, and occupies 1 liter, and calculate the moles. All right, so what are you seeing there? You're seeing pressure, volume, temperature, and moles. So although it doesn't have the heading ideal gas law problem, it is an ideal gas law problem. All right, and we have a pressure. It is in atmospheres. All right, I'm checking. That's in atmospheres. This unit is in atmospheres. This, every one of these parameters has to be expressed in these units. So pressure has to be atmospheres. Volume has to be liters. What do we have? 1 liter. Moles is unknown. Temperature, 27 centigrade. So what do we have to do to that? Okay, now go ahead and get N all by itself. Take PV equals nRT, rearrange that to get N equals what? I mean, don't give me the number, give me the equation. Rearrange that equation.
So PV. Yeah, equals that.
Is this what we do? All right, I get problems, I get people bringing this back to me and they're saying N equals RT over PV. I don't know how they get there, but you gotta do it this way. And then plug everything in. Is this right?
Yes. That's what I got. You know if I got it.
So, I have a question. So, are these the only gas laws that we worried about? Like, there was another one on Newton. I said, Guy
Lussac or something?
Yeah.
No, yeah, don't worry about that one. The only other one, there is the Dalton's law of partial pressures. Yeah, that, don't worry about Guy Lussac at all. Folks on, Lucas is telling me on the Newton there was another law, the Guy Lussac's law. Don't worry about that law. It may be in Newton, but you won't have problems on that. Yeah.
Yeah, I was gonna say yes. Yeah. It's
Yeah.
Mark, I'm getting,
What did I do?
I don't know what you did.
It's just one.
If you do the top and the bottom, I got 0.04. It's not that.
0.04 moles?
Yes.
Point z-
If you want to continue, it's like a long number. It's like 0.04060089.
So
0.04 what?
Or 1.
I would have just taken that.
Yeah, I got this.
Give me one more number.
Oh, then yeah, it's
0.406. 0.0406.
Okay, Mark, go ahead and do it again.
I did. That's what I got. I don't know what you're talking about.
24.6?
No. I got the other one.
Ugh.
I think it's how, like, you place it and the calculator.
All right.
I don't know how you do it in the
If you get
calculator.
it separately, PV, you get that one, and then you get RT, that one, and then you divide those answers, and you would get, or 20.
Right. Okay. Yeah, you gotta divide by 300, not multiply by 300.
Yeah.
Right. You gotta divide by 300. Great. Thank you. Okay, let me write a problem here. This is going to be a calculate the volume of 1 mole of an ideal gas. Oh, wait a second. I got to introduce one other thing. Ideal gas at 273 Kelvin and 1 atmosphere. Hang on one second. I want to introduce you to a term. This STP. What does that stand for? Stands for standard. Yeah. Standard temperature and pressure. Okay, you can see that temperature and pressure affects a gas. So when you talk about gases, it's kind of nice to have a standard reference of properties that you're comparing them to. Standard temperature is the freezing point of water. And standard pressure is the pressure at sea level. The typical pressure at sea level is 1 atmosphere. It does change. A hurricane comes in and that pressure goes down. A high pressure area comes in and the pressure goes up. So even at sea level, atmospheric pressure is fluctuating a little bit, but the average is 1 atmosphere. The freezing point of water is 273 Kelvin. So STP corresponds to 273 degrees Kelvin and 1 atmosphere of pressure. So let's rewrite this problem. What is the volume of 1 mole of an ideal gas at STP? Boy, do we have time to do this calculation? Do we? We're going to have 3 minutes. Okay, we'll start right there. You've introduced with STP. We do need to move on here. We need to get on from gases to what's the next module? Energy or no, solutions. All right, so we'll tie up gas laws and on Tuesday, and we'll start solutions. Module 9, is that right? Module 9? Yep. All right, but we'll start with this